Hi, thank you for your patience in attending my lectures. By the way, a younger speaker yesterday said thank you for listening. You should never do that because that's presuming your audience is listening. So I'm thanking you for your attendance. I was told this by an older mathematician, so pass it on. Point counting on poly n. I'm pounding this example into the ground for good reason, just to show that we're specializing this rep stability and counting everything. I'm specializing it to one example, the simplest example, and I'm showing you I could give 4 lectures on it, and I could give 100 more lectures. And a friend of mine said, yes, this topic is inexhaustible. So let me just recall where we were last time. I have a general theorem. And it's the Grothendieck-Lefschetz fixed point theorem, sometimes called the Grothendieck-Lefschetz trace formula. And maybe I'll say it in the context. It's often stated for smooth and projective varieties, but we don't have a projective variety. We don't have anything that's compact. So let me state the general thing. X in algebraic variety, and let me assume it's a manifold, so smooth, but not necessarily compact, defined over Z, say. Then, on the one hand, you can look at the number of FQ points of your variety. That's point counting. And on the other hand, here's the formula. It's summation minus 1 to the I. It's like the Lefschetz fixed point formula. The trace of your morphism, of your self-map, going from the ith cohomology. Now I want compactly supported and étal. So I'm going to put C comma étal, whatever that is. I'll write the things. It's X, and you're reminding yourself it's like thinking about over FQ bar, and just to show you and whack you out, it's going to be like, you have to use L-adic coefficients. It doesn't matter. It's just a vector space here. So there it is. So far, this is still actually really good, but how do you compute this in practice? Now, Deligne, so there's 2 steps. He showed, well, let me just do it in our case, because it's easier. So how to compute? It's 2 steps. Step number 1 is you need to find, how do you compute the trace of a matrix? You want to find the eigenvalues of Frobenius on these cohomology groups. For us, by work of Deligne and in this case like Lehrer, and I'm probably forgetting names. No. Each eigenvalue, they're all the same, which is actually, that part's reasonably common, I think. Each eigenvalue is Q. How can I say this? Do I want to... Sorry, let me just think for one moment, please. Which parts of the story? What's secretly happening is I want to use, there's secretly like a Poincare duality, because I want to get rid of compact support, and but let me say each eigenvalue, I'm going to apply like Poincare duality. I'm going to erase compact support. I'm going to take a dual, don't worry about that. And to do it, it's Q to the dimension of your variety minus, so when I say for us, I mean X is poly sub n. The dimension of the variety poly sub n, its dimension is n, its complex dimension. So the answer you get is q to the n minus I. So I have some matrix. It's a linear algebra thing. The field happens to be QL. Doesn't matter. All the eigenvalues are q to the n minus I. What this means, when you have a matrix, and if the eigenvalues are q to the n minus I, this is on HI. This implies, I'm thinking of it as diagonal matrix in this picture, but if all the eigenvalues are q to the n minus I, this means that the trace, this trace of this mystery thing, is just q to the n minus I times the dimension. Right? You just take out the q to the n minus I. And the trace here is going to be q to the n minus I times the size of the matrix. So it's just the dimension of this mystery ith et al. Cohomology group. That's step one. So we just have to do this. But step two is, and there's all these hypotheses, and our case is special, but there's something called the comparison theorem, and this is where a lot of the magic happens. And this kind of thing is due to Artin and Grothendieck, Artin-Grothendieck. And here's the awesomeness. It's that HI, this mystery et al. Cohomology of x over fq bar, with L-adic coefficients, QL, the dimension as a vector space over QL equals the dimension as a vector space over Q of just good old-fashioned cohomology of our manifold with rational coefficients. This is totally arithmetic. This is totally topological. So that's a super deep, hard stuff. But it's true. And so the upshot for x equals poly n is the following formula. And the formula is that the number of polynomials, the number of fq points of this variety, is an alternating sum of, you take q to the n minus I times just the ith Beatty number of the space of polynomials, ith rational Beatty number. That's the dimension, just so I don't have to keep writing that, dimension of HI over Q. It's dimension as a rational vector space. So any questions?
So I could plug in the Braid group there, right?
Oh, yes, sorry. I should mention that for people who prefer the Braid group, poly n is a k-pi1 space for the Braid group, right? The fundamental group of poly n is the Braid group, which we talked about yesterday. All the higher homotopy groups vanish because the universal cover of the space of polynomials, it's a hyperplane comp. You have to prove it, but all the higher homotopy groups vanish. And so this happens to be, side comment, bi of the Braid group on n strands. Exactly. So the cohomology of the Braid group has to do with polynomials in this way. So let's just do it. Let's just, and here's what it is. And by the way, you can, there's one of the first theorems, and it's due to Arnauld in 1968. He computed the cohomology of Bn with rational coefficients to be Q if in degree 0 you have a connected space, and in degree 1 there's one cohomology class. Here's what it is. Ready? What's something in H1? It attaches to each element of my group. Let's do it homology of the Braid group. Or homology of n configure. Yeah, let's do the Braid group. It attaches to every braid a number in a way that's additive. Ready? Number of overcrossings minus number of undercrossings. It's a winding number in the space of polynomials. And it's 0 for I greater than 1. And this is for n at least 2, I believe. You're already seeing stability because when n is 1, the cohomology is a little different. So let's plug this in and see what we get. I love super hard theorems with super easy things because they usually illustrate. They're illustrative. And in this case, not in all cases, you can go the other way on the magic bridge And you can use the high school computation of the left side to determine, this is only in very special cases, you can use it to determine the cohomology. There's this kind of going back and forth on the bridge, which I'll talk more about tomorrow. Yeah. So just plug in. So plug in Arnold. To Grothendieck-Lefschetz. And what do you get? You get that the number of polynomials over FQ. So I'm giving you a proof of concept that this stuff is actually usable. That's the left side. You have an alternating sum from I equals 0 to the dimension. But all of these terms are 0 except when I equals 1 and I equals 0 and I equals 1, right? That's what Arnold told us. The Beatty numbers are all 0 except for I equals 0 and I equals 1. So when I equals 0, I plug in 0. I get minus 1 to the 0. I get q to the n times the first Beatty number, which is 1, minus, and it's q to the n minus I is 1, q to the n minus 1 times the first Beatty number, which is 1. And then plus 0 minus 0 plus 0. So it's q to the n minus q to the n minus 1. And that is the actual count. I'll actually probably give another proof tomorrow, actually, from a different point of view. So any questions? Conversely, it's a little harder. In general, it's much harder than what I'm saying. But if I asked, Yoav, tell me the number of, compute the left side for me, he could surely do it. And he would say it's q to the n minus q to the n minus 1. And I would say, oh, you know what I see here? I see h0. I could get Arnold's theorem from that. I literally could prove Arnold's theorem from that calculation, quoting this étale cohomology stuff. And I think in modern number theory, it's much more common to use the left side to compute the right. OK, any questions? So I now want to tell you about the twisted story, which is much, much richer. Great. OK. A little better board work. So I want to talk about twisted. This is a super beautiful picture. I love this picture. And weighted point counts. And the theme here is going to be we can understand a lot more than just how many polynomials are there. We can actually try to say what do all the polynomials look like by understanding the cohomology better and better. And this is where representation theory comes in. But let me give you the topology picture. Here's a beautiful vector bundle, a very natural vector bundle over the space of polynomials. It's a n-dimensional complex vector bundle. I'll just call this like E sub n. And what it is, here's like, say, the space of polynomials over C. Everything's over C. And over a polynomial P, I can just put the vector space, I'll call it V sub P, and define it to be just the free vector space, the C-span, on the set of roots of P. And since my roots are all distinct, this gives me an actual vector bundle. Right? Any questions? And what happens as you move around in a loop, this space has topology. I should draw it like that. That's the only manifold any of us can draw. Maybe some of the three-manifold people would beg to differ. As I move around and I take a path, P sub t, of polynomials beginning and ending at my polynomial, at each stage, of course, I have the roots, and I can keep track of the roots. Locally, of a locally trivial fiber bundle. This is even a flat one for the experts. And I'm like, and locally, see, you can tell if the roots are distinct. If our roots are like 1, 2, and 3, when you move around in the space of polynomials, you move the coefficients. Now the new roots are like 1.1, 2.1, and 3.1. You can still match up which one was which. So that's essentially a proof that this is a flat vector bundle. Anyway, you get this vector bundle, and when you come back, the roots have moved around, perhaps. So you get an action on V. So what's happening is you get an action from pi1 of poly n, which is the braid group, to GL of C to the n. In other words, GLNC. GL of, to be more specific, this is like GL of V sub P, which is just GLNC when you pick a basis. So any questions? You get this representation. This is describing, this is called the monodromy of the vector bundle. And in fact, we know it factors through a representation of the symmetric group. Because it's just, we're just keeping track of, you're just permuting what happens to the roots. You don't take the first root goes to the first plus the second. You're just permuting them. So any questions? Okay. And this representation, if V has basis, like if the roots are like E1 to En, this representation just takes a permutation, and the permutation is acting, it's just a permutation representation. It takes the ith 1 to the sigma of ith, okay? So it's a very cool vector bundle. What I'm going to do is I'm basically giving a little crash course on cohomology with coefficients, with local coefficients, in a local coefficient system, or sometimes called twisted cohomology. And what is it good for? I want to show you what twisted cohomology is good for. And once you see it, you can never go back to constant coefficients. Yeah, so sometimes, now with these, for some examples, you can give an interpretation, and I can talk to you about this after, using like the Leray or Hochschild-Sayre spectral sequence. Sometimes when we're going to talk about cohomology with twisted coefficients, it's the cohomology with trivial coefficients of some other space. Typically you have like a family of, anyway, sorry, I better stop with that, yeah. Oh, we'll talk after, yeah. But it's not always. Or sometimes you're trying to find that space to interpret. Yeah. Okay, so you with me here? I want to relate this to point counting. So now we're going to jump into the world where we have poly n of f q bar. This is the algebraic picture, or arithmetic picture. Poly n of fq. Frobenius is acting. Sitting in there is the fixed set of Frobenius. That's called the degree n polynomials over fq. That's what we computed last time, right? We found the fixed set of Frobenius. This is equal to the fixed set of Frobenius. So guess what I'm going to do? Given any polynomial, even any polynomial in this whole space, any polynomial p, now for the experts, I'm aware that you're doing like, I'm taking an L-adic sheaf and da-da-da, but just, I'm going to do lies to the audience, but these are very good lies, because you can actually use them and prove things, and then find out later you can like justify. Sorry, I mean like finding the answers is just as important, yeah. But I mean, proving it is important. But I'm going to now take a vector space, the C-span or Q-span. Let me take the Q-span. We could have done the Q-span over here. Given P, I'm going to just stick a vector space over that point. And I'm just going to take V sub P to be defined to be the Q-span, or it could be, I'll just take the Q-span of the roots of P. Yep, P is now a polynomial over FQ. But it still has n distinct roots if it's, right? Now, there's no monodromy or anything like that anymore, right? But let me tell you what the, no. They're all in FQ bar, yeah. So, let me show you how Frobenius, so Frobenius is acting on this picture, really in the same way, but at the very least, Frobenius fixes P, you can sort of create a vector bundle here, but you can use this set of roots to encode information. Let me say how, exactly. Let me give an example. I think this really helps it come to life. Let's consider p of x is x squared plus 1, and let's think about it in just like f3 of x. And like I said before, yeah, you have f3. That doesn't have any solutions. So in f3 squared, this is the roots epsilon and minus epsilon. Right? If epsilon is a root, then so is root minus epsilon. So what's happening here is the following. You have this filtration of the space poly n fq. There's fq squared points, fq cubed, right? These are lying in the fq squared. And what happens is Frobenius fixes. So Frobenius 3, it takes x goes to x cubed. You know, I should call it like z goes to z cubed. It takes a number and takes it to its cube. So for Frob 3, it fixes. So P is in the fixed set of Frob 3. The coefficients are fixed. The coefficients of this polynomial are 1 and 1. And 1 is fixed by Frobenius. But the roots are not. What does Frobenius do to the roots of epsilon? Right? So Frobenius is acting on the whole thing. It's fixing these individual points. So you're not going to see anything else. If you're asking me, like, what more can I see just from this set? Yes, you're acting by identity on this set. With this vector bundle stuff, it's supposed to encode what I'm doing now. And Frobenius acts on the roots. It takes epsilon to epsilon cubed. But epsilon cubed, epsilon squared is equal to minus 1. So this is minus epsilon. And minus epsilon goes to minus epsilon cubed, goes to epsilon. So the cool thing is Frobenius 3 acts on v sub p by a transposition, 1, 2. It switches the two roots. Any questions? Now you might complain like you were labeling things, you're making choices of bases. Yes, but if you chose a different basis, maybe it's acting by 2, 1 instead of 1, 2. Or, okay, if there were more roots, you know what I mean? Like 1, 3 instead of 1, 2. Up to conjugacy. So the conjugacy type, well defined. So one more little thing, for example, is that if you take p of x equals x minus 1, x squared plus 1, and this is fun to x cubed minus x squared plus x plus 1, sitting inside f3 of x. It's a degree 6 polynomial. Frobenius fixes this. Frob 3, acting on poly sub 6, because the coefficients are all like fixed by Frobenius. They're all in f3. But here's what you're doing. Here the root is in fq. Here this is irreducible. You just check. There's no factors in fq. There's no roots in fq. And this is irreducible. So this is an irreducible quadratic, and here's an irreducible cubic. And the picture is that you have that epsilon and minus epsilon are still roots. But now you have like a delta f3 cubed. You have an irreducible of degree 3. It's got like delta and delta squared and delta cubed are the roots, right? And so here what's happening is that Frobenius 3 induces a permutation of the roots of the set of roots of P. And let's call it, I'm going to call this from now on the permutation you get from Frobenius. I'm going to call it sigma sub P, where P is the polynomial. It's just a permutation of n elements. Here it's 6 elements. In this case, I fix this element. I permute the two roots. And then here it's 4, 5, 6. There's 3 roots and they're being permuted. That's how it works. That's what you learn in algebra class. So any questions? No, it does, it's just the tower. It's not contained, yeah. It's just the tower. It's where each one is like a vector space. I mean, there is a container. Sorry, yes, it's not that it's sitting above. Right, it's a vector space over F3. That's all I mean. So what's happening I just wanted to sort of do this by hand so you get a feel for the Frobenius and how it's acting. And I'll probably have to make some kind of a jump. Sorry, what time is the end point again? Wow, OK. I thought I'd been up here for like 2 minutes. So note the number of linear factors. So for a polynomial over FQ, the number of linear factors, so for a polynomial P, corresponds to the number of one cycles of the permutation sigma P. The number of quadratic factors corresponds to the number of two cycles, right? And so let me just tell you what the twisted Grothendieck-Lefschetz formula gives. And what it gives is let V equal any representation of, let's say, Sn. Or for experts, you just need a virtual representation. That's what you really want, a linear combination. You really just want a class function. A virtual representation of Sn. And so pi1 of polynomials acts on it by first going to Sn, and you act. Let me just give the formula, and then I'll use it, and you'll see what I'm doing. The sum over fixed points of Frobenius, which are the polynomials over FQ. And now I'm summing the character of the permutation. That's the left side. That's an alternating sum of, let me do it this way. Q, do I want Q? Yes, Q to the n minus I times the ith Beatty number, the complex world. Times the dimension of the ith cohomology. It's just like the classical formula, but now with these twisted coefficients. You can always put here a module over this group. That's the formula. So for example, when V is the trivial representation, what are you counting? So I think of it like this. I have a bunch of polynomials here. Ready? I first want to count how many are there. I can build this vector bundle. One-dimensional one. Let me build a one-dimensional one. The character, so here's a irreducible representation of the symmetric group. Everything acts by the identity. That's the trivial representation.
Wait, sorry, because the sigma P is Rob acting on the fiber?
No, this is the fixed points of, no, this is sum over fixed points of Frobenius acting on, this is equal to this polynomials, poly n of FQ. The action on the vector space is this trace, chi sub V, or V sub P, yes, thank you. Like sort of the character of the representation there.
Sigma P is Frobenius acting on the fiber.
Yes, sigma of P is Frobenius acting on the fiber. So when everything is acting trivially, it's a 1-by-1 matrix with entry 1. So you're adding 1 for each polynomial. And on the other side, V is just constant coefficient, C. You get the classical case. So V is C triv implies chi sub V is just 1, identically 1, implies the classical. So you think of this as you're like counting points, and you're weighting them each by 1. But now, what if I just plugged in blindly to this formula? Suppose I plugged in the one that I just said. V is C to the n, the permutation representation. Sigma dot EI is E sub sigma vi. What you get, remember the character, that's the trace of the matrix of any permutation It's the number of fixed points, right? Which is just the number of one cycles of my permutation. Right? The number of fixed points, it's the number of one cycles. So what I'm getting out of this formula is that the left-hand side, so the left-hand side, I'm adding up for each polynomial over FQ. This is the number of fixed points of Frobenius, the number of one cycles. That's the number of linear factors. I can do all these other things. What are the higher moments of this? So the expected number of linear factors is like, this counts the total number of linear factors over all polynomials. So if you want the expectation, you divide by the number of polynomials, which is q to the n minus q to the n minus 1. Ready? You want to know the higher moments of this? Just cube it, square it, cube it to the fourth. I'm running out of time, and so you can plug in, what I want to say is you can plug in any class function on the group. Anything that only depends on the conjugacy class. And there's the fundamental observation is that when you have a polynomial and you factor it over FQ, you factor it into linear factors, quadratic, cubic, etc. The way Frobenius acts is by a permutation. And that permutation has 1 cycles, 2 cycles, 3 cycles, and they exactly correspond to the linear factors, quadratic factors, irreducible quadratics. So now, let me just give, though, so the thing that we need to compute now is this. Now, this is where we have to pay the piper. And these counts you can do. Number theorists can do them. In our paper, we start doing more and more complicated ones, and you start to need like L functions, and so it's not totally easy. They get harder and harder. But maybe I'll just give our theorem. Yeah, so how to compute that? It's all about this twisted coefficients. But all I want to say is from this, twisted coefficients correspond to weighted point counts. And the way I think about it is, ready? Instead of weighting them as 1, here, what does it mean? You're weighting it by a character. Here's a class function on the group. Each polynomial, I'm going to weight it by the number of linear factors. Right? So this one I weight 1, maybe this has 2 linear factors, maybe this has 0, and I just do the same count, but I'm counting. If you want to know the number of quadratic factors, ready? Or no, you want to know, like, let's weight it by, let's just count the number of guys that have no quadratic factors. Ready? I just go, and I look for guys that don't have quadratic factors. I'm going to weight them by 1. The others I weight by 0. That's a class function. Because no quadratic factors is like no transpositions. There's like a dictionary. And so for every weight, you get a different theorem. And you get like natural theorems. Like when you put in the sign representation, it's like, tells you about like the discriminant. It's a whole big dictionary that's in our paper. So let me just tell you though the final, the punchlines. Okay, but any questions? I think it was really worth doing this one example very carefully. Because you can see you can start going to town. But I want to connect this up with representation stability. And to me, this was a very exciting application of finding these specific patterns. And I think there's yeah. Again, I guess we're not claiming that we're giving a new theorem, that it's a new theorem in number theory that we computed the number of linear factors. No individual thing, like a number theorist could do it. That wasn't the point of our paper. It's the bridge. It's the connection between stability arising and these kind of arithmetic statistics and stability arising in cohomology. So let me give how to compute this twisted cohomology of the Braid group or poly n with coefficients in some Sn representation. All my representations are going to factor through the symmetric group. And how to do it, it's just, there's a transfer lemma. It's the same as classical transfer, which is like averaging. You're using the fact that our space of polynomials is also the space of unordered configurations of endpoints. In the plane, we have this very natural cover, and various people, including me, have been talking about the cohomology of this, like in Vic Reiner's talk. And the transfer says the dimension of this twisted cohomology group, which is what we want to compute. By the way, notice I've already used the miracle. We're still just in manifolds world now. I'm forgetting about étale stuff. The left hand is the étale count, you know, the finite field stuff. The right hand is still manifolds world. Can you tell me when I have 5 minutes left? The dimension of this is equal to, I'm just going to write it first. It's, you look at the cohomology of the cover with trivial coefficients, and you look at the inner product in Sn with V, inner product of representations. What this means, let me just tell you, if this is an irreducible representation, this is just the multiplicity of V in here. How often did this occur? So like in Vic Reiner's talk, he was talking about these V of lambdas, these irreducibles. So like, and in fact, computing any of these, it's enough to do it for irreducibles. So now you need to know, what is this with coefficients in V of lambda? Well, decompose this into a sum of irreducibles. It's V, you know, V of this partition to the first power, V of lambda to which power? That's what this is. Okay? There's 1 over, sorry, like 1 over the order of Sn. Is that, oh no, it's inner product, so there's not, anyway, yes.
Generically, it would be the V dual, right? But the point is
Yes, there's a dual, yes, generically there's a V dual that I'm hiding. Yes, you're using that things are self-dual, yeah. But that's what this representation stability is about. Remember I promised you, why do I care about this as a representation? One of the reasons is it encodes and is encoded by, like the decomposition of this into irreducibles is literally, I'm asking you, what's the right-hand side here? Which by transfer is what's the left-hand side here? Which by super deep stuff are these point counts? So right there, that's what it is. So let me state our theorem. By the way, for example, before I just do it, I have to give one thing. Example, you can compute that the ith cohomology of configurations, this is the thing I've been talking about forever, of ordered n tuples. Maybe I'll say it this way. The inner product, this kind of this is not quite an irreducible. This is a sum of two irreducibles. This is the inner product with the permutation representation. This is equal to, I mean, you have to figure out how to do this, but this is like basically like the topic of Vic Reiner's talk, for example, and our very earlier papers. And, but this is something topologists can do. Greater than or equal to I plus 2. So now I just plug this into that formula, and the expected number of linear factors of a random polynomial, monic square-free polynomial in FQ, is equal to sort of the total number over all polynomials divided by the number of such polynomials. So you have to mess around with the formula, right? We're going to have alternating sums of q to different things, and then this thing here is going to be q to the n minus q to the n minus 1. You might say, why do you keep dividing? Just give me the top. It's like, because that doesn't have as fun of an interpretation. And you end up getting 1 minus 1 over q plus 1 over q squared minus dot 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 plus or minus 1 over. That's like, in this case, we're getting like an exact count because we can do this exactly. So this is like a number theory thing. You can do it. It gets a little harder, but then other ones get really hard. But you can do them with like the theory of L functions and stuff. But it's the bridge that's important. So any questions? So now, yes?
when
Exactly, exactly. So, right, there's like a trivial plus the standard, and then you have to figure those out, and yeah. Oh, I'd have to, let me talk to you after about that, because that's like, I'd have to like stop and like think and rethink the whole, right. But what I love too is that this gives you predictions. Your question's a really good one too, because you can often, if I can compute the arithmetic part, then you can start trying to predict which things occurred. And sometimes you can prove such things. But let me give you our meta theorem. Again, this is still all joint with Jordan Ellenberg. This is Church-Ellenberg and Farb. Sorry, I think it's fake humility to do the F. And it's called, we call it like stability of polynomial statistics. And here's the general form of the theorem. I'm now going to prove all such theorems for all counting problems, at least if they have an answer. So let P be in, think of it, take a polynomial in x1, x2, where xi equals number of I cycles. So one way to get a class function on a group, and this is a basis for all class functions, I'm just switching bases. Instead of irreducible representations, I'm going to talk about class functions. If you give me something like x1 squared minus 2x2 or something plus x7, that is a class function. It's a constant conjugate classes on all symmetric groups at the same time. You give me a permutation, I just take the number of 1 cycles and square it, minus 2 times the number of 2 cycles, plus the number of 7 cycles. Okay? If you give me a polynomial, and you want me to factor it over FQ, this is going to tell me the square of the number of linear factors, subtract twice the number of quadratic factors, and add the number of degree 7 irreducible factors. Right? If I like plug this in, I of course erased it, but I had this sum over characters. I can just take a sum over these things. So then the limit, I'm going to say this in like FI module way for people who are, you can take the cohomology of the FI module conf dot, and I'm going to, of C with coefficients in Q, and the multiplicity, sort of the inner product with this polynomial. I'm going to define this to be, let me just write it down first and then I'll comment. A limit as n approaches infinity of these multiplicities of the character, sorry, it's the character of this. You know what I mean? Of conf and C, Sn, sorry. So this limit exists. So what does this limit mean? This is like, look, we took the standard representation, the permutation rep. Notice here you have this stability result. For each fixed I, as n gets big, I think that's true, yeah. This limit exists as n approaches infinity. I'm defining it to equal that, sorry, to equal this limit. And in fact, the right-hand side is constant for n greater than or equal to 2i plus degree of your polynomial. I'll comment on this in a second. Further, for all primes q, the following limit actually exists. And we have in our paper all these examples. So you should think about this over here as an example. I'm going to tell you that, like, as the degree goes to infinity, this converges to a power series. Limit as n approaches infinity, and you're adding up the total number of things. Oh, I should not have called that P. P of f. F is a polynomial over fq. Sorry. And this is going to be this alternating sum times that side. Thank you. And in particular, both of these limits, the limits exist on both sides. So what I'm saying is, any counting problem you throw at us, like the number of linear factors, quadratic, any kind of thing like that, polynomial statistics, it's like only depends on sort of the irreducible decomposition. Any such statistic you throw at me, there exists an answer, there exists a limiting thing, and it converges even like in formal power series. Of course, you need to compute those, that's a different matter, what the answers are. But this is representation stability. The proof, the statement that this converges, this is representation stability for cohomology of configuration spaces on C. And I don't have time, so let me just say, in conclusion, we have this dictionary, and there are more entries, but I hope I showed you at least all this representation stability stuff. I specialized to the easiest known case in the very first case we did, and just that it has this like very deep connection, and I think a very beautiful connection to point counts, and you see it in there. And so like, go forth and do all the other examples. I mean, you know, they should also be rich. So on this side you have arithmetic, on this side you have topology, and you have like the point counts for a variety. And here you have the cohomology. You have to understand the cohomology, even just rationally, of the complex points of your variety. That's the classical. The twisted, the classical. But if you only know this, if you don't know the cohomology, if you have homological stability, classical homological stability, you only know the homology groups, or the cohomology groups stably, you get asymptotic point counts, meaning asymptotic point counts for sequences. You're looking at the number of points in, like, you have a parameterized sequence of spaces, like poly sub n, and maybe you don't, we happen to get it exactly, but in general you're going to find a harder time. But whenever you have homological stability, you should get asymptotic point counts. This is a very, very new idea in this dictionary. It's implicit in other people's work, but I do think it's like you can read Venkatesh's ICM talk from 4 years ago. It's Westerland, Venkatesh, and Ellenberg. But now I think there's a new entry, which is asymptotic point counts. Just tells you how many polynomials there are. How about all these like weighted, asymptotically, or sometimes exact. I gave you exact ones. Weighted point counts. Asymptotic meaning in n. And here is representation stability. And literally, you can, like Wei-An Chen, give another proof of representation stability for like the pure Braid group, just as a proof of concept. He just did the damn counts showed counts had convergent answers, and then he gets representation stability. So it really can go back and forth. And my next talk, I'm going to talk sort of a different, starting from scratch, and like a lift of everything, like reasons why point counts on one side are true and they look like the computations in cohomology. But I'll leave it there. Thank you. Oh, good. To the second, I got it. Not.
So there's a lot of interesting representations of the Braid group that don't factor into the symmetric group. What can you say about those?
Yeah, so what Andy's saying is, just to, this whole game was like, look, I have conf n, and it covers the space of polynomials, and I have Sn, right? And here you have like the Braid group, here you have the pure Braid group as the fundamental group. And we did this whole game, but I'm only measuring the permutations. Again, shouldn't we learn from McMullen's work and other people's work, like, you should just look at the braids themselves. Like, why are you just looking at permutations? And I would say, because we're really wimpy. But it's also because, and we had like representation stability. What you want to do is, the Braid group has many other interesting representations. And those absolutely give you super deep things, and it's a very beautiful picture that I can explain right after. But better, Wei-An Chen is here, who's right behind you. He computed, you have to compute these twisted cohomology groups, which is tough. But he computed cohomology of the Braid group with coefficients in the Borel representation. It was great. And then he used that to give it, sorry, I hope I'm not announcing before you, anyway, too late. Theorem, I'll put it in quotes just in case, but use that to prove a beautiful theorem that says you actually take the number of like hyperelliptic curves of genus G, like what's the average number of FQ points? And that's a little different. This is like over all curves. You're integrating over like some modular. And it really has to do with this, believe it or not, because there are branch covers. And he gets the exact calculation. And what's cool is, in many cases, we don't know the actual numbers of the individual things. He just computed the average, right? Number theorists, there's hundreds of papers computing all the exact things in different. So he just but anyway, so there's this huge dictionary, and topologists can absolutely say stuff. Those guys couldn't do it because you have to compute. You have to understand like the Borel representation and get access via the topology. So that's a great question. I think that's a great direction for the future. All of this is just the symmetric group. There's tons more stuff, and just for this space. I will say, too, in these point counts, I just have to say it is so cool to see on a computer. You know, when I wrote, some of the more interesting ones have like 1, it's the number of blahs, and you see like 1 over this plus 17 over q to the 4th. What's really great, when n is 2, these numbers are different. 3, the numbers keep changing, and then the numbers, like the coefficients, like stabilize. That's what our theorem gives, is that you get a power series. But only for large n. So again, like the second term of the power series, it starts out like 0 over q cubed, then 1 over q cubed for what, and then it's like stability in another direction.
Could you prove like these stability ranges using these point counts, like to give these?
So the question was, could you prove stability ranges using point counts? Yes. And actually, the one thing in the dictionary that I didn't say is that here the stable range, in the terms of stable range, either like even classical homological stability, that corresponds to, that has meaning on the arithmetic side, and that's like how fast are these power series converging. And we have like exact bounds. It's like, yeah, we have bounds. So when Vic Reiner gave a sharp thing for the stability, Hirsch and Reiner have given this sharp stable range. That has this added application. Other than being interesting, intrinsically interesting, they're showing that like, here's the error term, and it probably means the error term is like the best possible. So I love this, 'cause I haven't seen, have people seen before stable range having an application? I mean, the application of stable range is like, look, if I want to know the 15th homology of the mapping class group, I only have to look up, I have to just do it for genus 30. And then I get all genuses bigger than that, or whatever. Cool, it's a finite, but the actual number of stable range, people are always trying to improve it. Are there other applications? I mean, I got excited by this just because like, here's an application like outside of topology of stable range.
So you only use rational information on the topology side. Like there's also interesting topology as well.
Yes. So this is the thing. Whenever we talk to topologists, I was telling Jeremy earlier, actually, I was thinking of you and Jeremy, a little insecure in front of you guys, because like they really know so much very deeply the structure of cohomology, and we're coming in and just like doing rational, which a self-respecting topologist wouldn't do. But I'm neither a algebraic topologist nor am I self-respecting. Integral information. And in number theory, this has been a thing, and Venkatesh is like one of the world leaders in that. Arithmetic information about like torsion. That's a whole new story in recent story, I think, in number theory. In this étale stuff, as far as I know, they still don't, meaning the étale number theorists don't know how to use. I don't know of a place where they know how to use integral information. Clearly, since it's carrying more stuff, it must be able to tell you much deeper things. I have a feeling, maybe Jesse could answer this. Is this like Voevodsky's theory of motives is trying to like get at that, or is there?
There's stuff in this direction, like the motivic homology is using integral coefficients, and like I know that like Marco Walk is like a quadratic refinement of Brody-Lefschetz for like motivic homology, so like probably there's something there, but like, I don't
Right.
know. I think like applications of point counting.
Right.
I don't know about that.
But that would be an exciting place for like the hardcore, the people who can do integral calculations.
What about even like FL? Some other,
Yeah, no, even FL, right. FL, secretly FL is occurring in this picture too, but FL, no, I don't know. So anyway, it's a great question. This is, yeah.
So like someone like Fred Cohen would say like, oh, if you're in homology, the thing that was on the board before this like is some part of like the free Gerstenhaber algebra on generator.
Mm-hmm.
And homology of all this extra structure, maybe it's not algebraic, maybe it's useless to you, but like
Yeah, that's another great direction that rationally people like Fred Cohen, the people who are algebraic topologists who do these great computations with various configuration spaces and stuff, they give, I'm just paraphrasing what you're saying just for the, that like, they do all this extra structure on like homology and all this other picture that's coming from topology and not arithmetic. That's tons of extra structure that we're just like ignoring. Does that have implications? Right. And it's hard to believe it wouldn't. So that seems like an exciting thing, but.